Okay, so hi everybody, welcome back. So yesterday, in the last 15-20 minutes, we managed to start discussions about convolutional neural network. So we will just quickly do a recap of what we discussed yesterday and then continue with CNN today. And today will be my last lecture in the preschool. Tomorrow, as far as I know about the plan, tomorrow there will be another lecture about CNN. It will be given by Professor Partho Kono. Okay, so yeah, so yesterday we discussed some basic building blocks of a convolutional neural network. So what we discussed, we'll just go through it very quickly, is that we need a filter, F cross F filter, which we use to convolve the image. And for very simple situations where you have a grayscale image, then you can decide what the filter would look like. Maybe you have an image which only have some railings, let's say, which means you will only have vertical structures and horizontal structures. In those cases, you can decide how your filters would look like. So just like this filter, which is a vertical edge detector. However, for complex problems, the one that would, let's say, as an example, car detector, the picture of car or picture of flower, this kind of things, those are more complex things and you cannot really decide on your own how your filters would look like. So in most realistic scenarios, what people do is people actually treat these numbers in the filters as parameters, which will be learned when you train the network. So this matrix here, W1 to W9, these parameters, this is a more realistic filter, although this kind of hand-picked filter can be used if you have a very simple image that your problem revolves around very simple images. Okay, then we discussed about padding. So you can choose to use zero padding, which means no padding, which has a name of valid convolution. So valid means no padding. And then another option is same convolution, which means that you can apply a padding to get back the output, which was the same as your input. So if you have a 6x6 image, you can use one layer of padding. And then if you have a 3x3 filter, you will get back the 6x6 output again. This is the concept of same convolution. Then we also discussed about strided convolution, which is how many units you will move your filter towards the right and downwards when you are doing the convolution operation. So generally stride of 1 is used, which is a very common choice. And you can choose to use stride more than 1. For example, stride 2 would look like this. Generally, our input picture is a square picture, so it's a square matrix, but it's not a really mandatory thing. So you can decide to, depending on how your image is, you can decide to have a non-square matrix as well. But for most of the examples that we will discuss today, you will see that people generally prefer to use a square matrix.
But I have a question. Like filter, this looks like a square matrix always.
Generally, people use a square filter. Yes, it's also not a hard and fast rule because you can still do this operation of convolution using a filter that is not square. But general practice is square filter.
But if it is a not non-square matrix, then we can add zero up in one row or on column,
Yeah,
we make a square matrix, right?
yes, yes, yes. That you can do always. So, so all the options are possible. The most common ones, the ones that I will discuss are the most common ones. But depending on your particular problem, you might choose differently than the most common practices. That is totally all right. Okay, then this is something we discussed. Okay, then we also discussed about RGB image. Most of the real life problems do not deal with the grayscale image. It deals with RGB image, which means that 6 cross 6, which is the height and width of your image, times 3, which is the number of channels. And in that case, you should also have a filter which is 3 cross 3 cross 3 or F cross F cross 3. So this 3 should match with this. So then moving on. So this is, we stopped at this slide yesterday. So now moving on to this. Clearly, when you have 3 layers of filters, because you have a RGB image as input, so you can think that the first one is red, second one is for green, and third one is for blue. Now, let's say you are interested to, you want your network to learn how to detect a vertical edge for the red color only, and you do not care about green and blue, then you can choose this filter as your first layer for red and all zeros for green and blue. This is I would say, rather rare choice. Generally, this is not done this way, but this is a possibility that one can choose. And if you want to detect vertical edge for all the 3 channels, so you care about vertical edge detection in general, then you would use the same values for each cell. So top left is 1 for all these 3 channels in the filter. So this is a more usual choice. So if we use the parameters W1, W2, W3, this like this. So generally we use W1 at the top left corner for all the 3 filters. Okay. Now about multiple filters. So these 3 channels, these are still just one filter. One filter because we are using W1 in all these 3 top left corner of these 3 channels. W2 in middle for all the 3, and W3 all in all the 3 cells. So these are essentially just one filter repeated 3 times. So one filter will be able to learn one pattern, but we are interested to learn various different kinds of complex pattern that might be present in the input picture. So that is why we generally use multiple filters. You can think about it as one is detecting vertical edge, another is detecting horizontal edge. Some will detect edges that are in some angle and so on. So then you will get an output 4 cross 4 matrix for one filter, another output 4 cross 4 for this filter, and then you stack them up. So eventually you get a 4 cross 4 cross some value. Here in this case it is 2. So this value here, this 2, represents that you have used 2 filters. Now moving on, so this is how one layer of CNN would look like. We have
Ma'am,
discussed, yeah,
the 4 cross 4 ones, are they the like the sum of the filters of 3 different colors?
yes.
Okay.
Oh, this is something, yeah. So you have 27 numbers here, and you multiply these 27 numbers with these 27 numbers in the top left, and you sum those 27 numbers, and that is the top left value here.
Okay.
Ma'am, if
Yes.
we use
general filter, like not vertical or horizontal, like all the elements in the filter are non-zero, then we don't need to use two types of filter, right? Like it will learn everything.
So generally what we have seen is that we need to use multiple filters because each filter has essentially only 9 parameters because they are repeated 2 times. So with only 9 parameters, it is not possible to learn very complex features in the input image. You need more parameters, and more parameters essentially means more filters. It depends on the complexity of your image.
Okay.
So we will discuss this, how complex it can get in some time. So now that we have discussed most of the building blocks of a convolutional neural network, now we can slowly try to build one layer of a CNN, and that would roughly look like this. So we have 6 by 6 by 3 input image, which is a colored picture. And let's say we have decided to use 2 filters, 3 cross 3 cross 3, and the other one is also the same dimension. Then we get a 4 cross 4 output from this filter, another 4 cross 4 output from this filter. So essentially what then we will do next is to add a bias term. So because what we have inside this filter is playing the role of W. So the filters actually play a role of W, the W that we discussed when we were discussing DNN. So, and the convolution operation of taking a filter and multiplying with this input image, that is as if we are doing a W1 times A0 kind of operation. So it's like W1 means parameter of layer 1 and A0 is essentially the X. So that operation is done and we get this 4 cross 4 matrix. So then just like before, we add a bias term, which is B1, and then we apply activation function on this. So generally, the activation function is ReLU for convolutional neural network. And once we do this operation, we get a 4 cross 4 matrix as the output. So these two 4 cross 4 matrices are then stacked together and we have a 4 cross 4 by 2 activation, and this is the A1. So if we just compare with what we had before for DNN and what we have now, this actually looks very similar. So the Z we had for layer 1, Z1 equal to W1 A0 plus B1. And here this is the W1 A0 plus B1. So this is actually what is drawn inside this bracket, that is as if your Z1, and activation function applied on that as if that is your A1 in our DNN terminology. But the good thing, yes.
Can you please mention once again that what is the like advantage of CNN over DNN that you have mentioned? But
Yes,
can you tell me once again?
I can definitely go back to that slide and mention that. So actually, it is totally okay to use DNN on images. So when you have image classification kind of problem, DNN can be used. The problem is that you will end up with a lot of input features. So the way the DNN works, you have a lot of, let's say you have, I have actually a better picture before. Let me go back. Yes, this is probably better. So here you can see it. that you have a picture here. And let's say this is a very small picture. Let's say we have a 64 by 64 image as an input. Then the number of features, if you use DNN, would be 64 times 64 times 3. So each and every cell here, these are the pixel intensity values, and 3 because it's a colored image. So 1, 2, 2, 8, 8. This is the total number of input features. So then accordingly, you will make your first hidden layer, which will have quite a lot of hidden units in order to learn the pattern of these inputs. So the number of parameters, the W parameters, becomes very, very, very big. Whereas in CNN, and this is what I'm going to discuss now, this is exactly the topic of this slide. Whereas in CNN, you only have this many parameters, and it doesn't matter how big your image is, you will have a fixed number of parameters, and that number of parameters is much smaller than what you would have for DNN. So because the way DNN is structured with all these fully connected hidden units, that makes the number of parameters too big to handle at some point. And if you are working on some problem where you are inputting just some variables and not images, then you can decide how many variables you will use as an input. You can decide to use 100 variables as input. But for an image, for a high resolution image, it very easily can go up to thousands or even some hundreds of thousand X or input features. Then accordingly, W1 will scale accordingly, W1 and WL in general. That problem is solved by CNN. CNN have much lower probability of overfitting. So you have only this many parameters as you see here. So 9 parameters here and 9 parameters here. You have 2 filters, so you have 9 plus 9 parameters, which is a very, very small number of parameters if you compare to DNN. So essentially, the overfitting problem will be better handled in this kind of network.
Okay, maybe a naive question that isn't it, can it be done that this filter thing, can it be done for DNNs also? Like, I am not telling that one-to-one, but some kind of like correspondence that I am filtering from CNN and some kind of operation I am doing in case of DNN so that it works like one-to-one.
The problem is that you need a image for this filter method to work, right? The filter is essentially a matrix, and your input image is also a matrix. And then you always need an image for the filter thing to work, and CNN works only on images. But DNN is something that has to work also on non-image problems. So that is the problem.
Okay.
Yeah, DNN has to deal with any kind of input, not only image, while CNN is a specific kind of network which deals with only images. So this is a specialized kind of neural network. Okay, so now moving on to the notations. This is something that you can. I will share my slides with Arun, who will upload it, and you will probably need it more when you will actually try to implement CNN from scratch. The notation will be important at that point. So generally, for filter size, we use the notation F superscript L for layer L. Then P superscript L is padding, SL is stride, NCL is number of filters in layer L. The input for layer L is NH L minus 1, L minus 1 because the input is coming from the previous layer, that is why L minus 1, but NH is the height, NW is the width, and NC is the number of channels it has. In the very first layer, if it is an RGB image, NC is always 3. But then once you have started to do the convolutions, then NC can basically be anything depending on how many filters you are using. And so this is the input, then the output is also denoted in the same way. And input and output dimensions will be related by this equation. Where is my cursor is gone? Yeah. So input and output will be related to this. This was discussed before. So depending on your padding and the size of the filter and size of the stride you are taking, depending on that, the output and input will be related in this fashion. And this is the filter. So FL times FL, so this is a square matrix, and then you have a number of channels that should match with the number of inputs. So NCL minus 1, this is matching with the input. Okay, now moving on. There are 3 types of layers in a realistic CNN. The one that we have already discussed is the convolution operation or convolution layer. There are 2 other things that we have to discuss before we can start to write down a proper CNN. So one is called pooling layer and another is called fully connected layer. Let's say what those are. So about pooling, this is a way to again shrink the dimension. So pooling layer is a layer which has 2 hyperparameters. One is F, which is the filter size, and S, which is the sprite, but it has no parameters to learn. That is a good thing. So what it does is that, let's say you have this input image and you are using filter size 2 and sprite size 2. Generally, these are the choices that people make. And there are 2 kinds of pooling. One is max pooling, one is average pooling. Generally, we use max pooling. It's more common. So max pooling is you put your filter 2x2 filter here in the top left, and you see what is the highest value here, highest pixel intensity, and that is 20 in this case. So 20 goes here in the output. Similarly, since stride is 2, then this box then gets shifted here. Box means the filter. And then here 30 is the maximum intensity. The 30 goes here. And this goes on for all the 4 blocks here. Here it's a small image, so it has only 4 blocks. So the output is 2x2 matrix here. Average pooling, as the name suggests, is the average of these numbers. So the pooling layer is used when you want to shrink the size of your input image. So the height and width of your image can be shrinked by using max pooling. And it tries to still preserve the feature by taking the maximum number. So maybe it has detected something, some contrasting thing or some objects. That information it tries to keep here. So now, if we can move on and try to discuss a proper typical CNN example, then that would look like this. We have an input image, which is this. Generally, the first layer is always a convolution layer with many filters. So as a result, you get outputs, but many outputs. And the number of outputs here just means that many filters were used. Then we followed by, so convolution layer is generally followed by a max pooling layer. And max pooling is again followed by a convolution layer, then another max pooling. So this is the general structure of a CNN. So conv followed by pooling, followed by conv, followed by pooling. And then at some point, you flatten it out, which just means that you roll out all the images. So let's say you have 4 digits here and another 4 digits here. So all these 4 digits will be written one after another, just like a DNN input. So 4 numbers here, then another 4 numbers here, these 4 numbers here, and this goes on until we reach the very last matrix. So this is called flatten. So as if we have the images and the pixel intensity values inside those matrices corresponding to the image, and we flatten them out here. After that, so after flattening, we get these blue colored blobs here. These are the flattened out version. And then we have a DNN-like structure. So we have a hidden layer with some amount of hidden units. And these flattened blue blobs, they are connected densely, or fully connected is another term for it, with these yellow blobs. And then finally, you have your output. The output structure depends on how many classes you have. Let's say you are doing a classification problem and you have 10 classes, then the output has to have 10 such blobs. Another thing to note is that in CNN, as we go deeper in the network, the height and width of your image representation decreases and number of channels increases. So the convolution operation and max pooling operation, these are decreasing the height and width, but you are using multiple filters, so that is increasing your number of channels. So this is a very typical structure of a CNN. Okay, now moving
Ma'am,
on.
after after max pooling, our data kind of got compressed. So then is it right to again operate convolution? Again operate a filter on it?
So this example, actually, it was a oversimplified example because the input is only 4 by 4. Generally, we will not have such a small input. We will have a much bigger matrix here. So max pooling output will not be this small. So
Okay.
yeah.
But ma'am, actually, my question was, let's say initially we wanted to filter out the vertical edges. We convoluted, then we use max pool, and then we want to detect the horizontal edges. So can we again operate the convolution on this output? I mean, will it preserve that information?
Yes, it actually preserves the information. Generally, when your network is learning complex things, so eventually you want your network to learn very complex patterns, but it cannot do that in one go in the first layer. Doesn't matter how many filter you will be using in your first layer. In the first layer, it will only learn to detect very simple things, like it can learn to detect a color or some pattern, some edge. So that information will be preserved by max pooling. Of course, one has to choose the filter size and stride carefully. But since it's a very simple pattern, that information is encoded in the highest number of a particular region. So then you can keep doing this thing again and again. And the convolution operation actually, once you do it deeper in the network, it will be able to learn more and more complex things.
Okay.
Now, in the max pooling, if we are using only the maximum values from a square, are we not losing the other values? I mean, if there, can you go back to the previous slide?
Yes.
Yeah. if in the first square box, if there were in place of 12, if there was 9 or something else, we wouldn't know because we are taking only the maximum values. So are we not losing the information from this?
So, of course, when we are doing the even when we are doing the convolution operation, we are losing some information. Max pooling also losing some information. So, the best way to not lose any information was to use deep neural network. However, it is a compromise between the number of parameters or number of inputs that you have to deal with, and the complexity of the network, the parameters, and how efficiently the network can learn. And it is difficult to intuitively understand why max pooling works even after losing the information of 3 boxes here. But actually, in reality, after a lot of research, of course, which came from the computer science domain, people actually showed that this works, and you decrease the number of the activations that you have to deal with, you decrease the number of parameters, and that actually helps the network to not overfit. So this has very positive effects on the learning.
Okay.
Hello.
Yes.
So is the filter size is similar or same for both convolution and max pooling throughout the training?
It's not necessary. That is not necessary. You can totally choose a different filter size.
Okay, and also is it remain constant up to the flattening?
No, not necessarily. You can choose different filter size at different stages, at different depths of your network.
Okay, so we have to back calculate it first, like at what step, what filter size we need to provide.
Yes, if you are building a convolution neural network from scratch, you need to have some calculation which will be based on this kind of things, input and output things. Yes, some computation will be necessary. However, I will discuss that it is probably better to not build your first CNN network from scratch. If it is your first endeavor in CNN, you can start with something which is a standard in this field, and then you play with it. So you first have a starting point, and then you modify the filter size and play with it.
Okay, thanks.
Hello.
Yes.
Like when we are training the network every time in the each iteration, do we need to like initialize the like convolution from different positions, like so that it can learn like randomly? Like what I'm trying to say, that let's say from the bigger picture, first time I am trying to do the convolution from the, let's say, left hand side, and then I am my starting point gets changed, and then if I do the thing, then it will be like generalized, right?
So the convolution operation always start by placing your filter at the top left, and then taking some steps depending on the stride, but taking your filter towards the right hand side and then towards the bottom. It's always from left to right and top to bottom. So you don't change your starting point, because even if you change your starting point, these values that you calculate, that will eventually be same. So probably it doesn't matter. But yeah, eventually this matrix, that's all it matters, from where you start. So wherever you start from, you will end up with the same values in these cells. So that's fine.
Yeah, important.
So, okay. Then, right. So this is a very typical structure of a CNN. And there are a few things that one might notice when building a CNN. So this is a table where you have in the left-hand side, you have all the operations written. So you are doing a convolution operation with some filter size and some stride size. Then you are doing a pooling, then again a convolution, again a pooling. Then you have a fully connected layer after flattening, and then you have another fully connected layer, and then you have your final layer, which is also called softmax if you are doing a multi-class classification. Your input images, let's say they were 32 by 32 by 3. So if you just multiply these three numbers, then you get the activation size. Activation size just means how many pixels you had in your input image. So number of parameters here is 0. Of course, it's just the input. So number of parameters come into play when you actually try to do some operation on the input image, which happens in the next step, which is the first convolution layer. So you have 5 filter size is 5 cross 5, stride size is 1. So that will shrink your input image to some value. Here it is 28 by 28 by 8. By 8 basically means that one has used 8 such filters. So then you can compute also the activation size and number of parameters, how many parameters you had. So it's a 5 cross 5 filter, and then you have used 8 of them. So that would be 200 W parameters, and then you have added B parameters in every of, so you had 8 filters, so 8 of those B parameters, so then 208. In pooling layer, the great thing about the pooling layer is that your network do not have to learn any parameter from the pooling layer. It has only the filter size and stride size, which are hyperparameters. In most cases, people just decide that beforehand by looking at the standard networks that has worked for people so far. So there is no parameter, and you manage to reduce the activation shape and activation size. Then you have another conv layer with 16 filters now. So, and then this goes on. So pooling layers have no parameters. This is one thing to note. Another thing to note is that the convolution layers have relatively few parameters. Most parameters that you see, if you just compute what is the total number of parameters in this very simple CNN example, most of the parameters are from the DNN-like layers, which are also called fully connected layers, just because the way this is structured, this is fully connected. So your W parameter depends on the number of hidden units by the number of activation coming from the layer before. So it's NL by N L minus 1, this kind of matrix. So that is why the number of parameters increases so rapidly. But here it just depends on the filter size. So conv layers have strikingly low number of parameters than fully connected layers. And another thing to note is that the activation size, this is just obtained by multiplying these things. Activation size goes down gradually as we go deeper in the network. If this drops very quickly, then generally that is not good for performance. This is one thing people have kept in mind while building the classic CNN networks, which I will discuss in a bit. Many convnets that you will encounter will have properties or patterns similar to this one. Those may be more deep. Those may have 10 conv layers than just 2 shown here, but the overall pattern will be the same. So now, yes.
Could you please go back? So how do we know the shape is going to flatten after pull 2?
This is your choice. When you will flatten it out, that is your choice. So you can have, you can decide to have a very deep network where you have conv1, conv2 until conv10 pool, and in between pool 1, pool 2, pool 10, and then you decide that, okay, at this point, I am happy, I will flatten it out. The amount of complexity that I have in my image, I am confident that 10 pooling layers and 10 conv layers will do. So that is your choice.
Okay, so again, this is for a single image, right? So the outer activation is a softmax, but why we have this 10 activation size? Is it a binary one, or you have 10 classes here?
So this activation size being 10 means there are 10 classes. If you are interested in a binary classification, it will just be one unit there.
Okay, okay, fine.
So here I will just mention some classic CNN architectures. The ones that I mentioned here are actually pretty old. Although AlexNet and VGG, some people still use those, but LeNet is actually pretty old, and people generally don't use those anymore. From the number of parameters, you can already understand that they are extremely big and deep CNN models. And it is actually very difficult to draw VGG in one single slide. There are so many steps that if I want to draw it in this fashion, it doesn't fit in one slide. However, I link here the papers in case you want to have a look. I would not recommend reading the LeNet paper. This is one of a little bit difficult to read. So all these papers are from computer science domain, so not exactly our cup of tea as physicists. We can still read the ones which are written in a more understandable language, which I would say is the AlexNet paper is one of those. If you really want to read the AlexNet paper. LeNet is also is very old and very difficult to read. VGG is somewhat in between. So LeNet had 60,000 parameters. AlexNet had 60 million parameters. VGG had 138 million parameters. So why are these important for high energy physics problems? Because none of those networks, they were invented for physics. They were invented for different other things, mostly face recognition or security, these kind of things, defense, these kind of things. So very advanced real life problems. That's why they have so many parameters. They have to learn extremely complex real life things. So why it is still important for us? So exploring the advanced CNN architectures as a source of prior knowledge, like AlexNet, VGG, they generally offer potential improvements to target model that conduct the AI-based tasks that we do in high energy physics. What kind of AI-based tasks we do in high energy physics is something we will discuss again in the later part. But let's say you have an object and you want to visualize how that object looks like in your detector in a eta phi plane. So what I'm saying now will be more understandable to experimentalists. So let's say you have a jet in your detector, let's say CMS detector, and you are plotting the image in the electromagnetic calorimeter in the eta phi plane. So that is the image representation, maybe HCal, not ECal since it's a jet. So it's the image representation of an object. So then if you want to know if your jet is a real jet or it's not exactly a real jet, it's a fake jet, some other object faking the jet, then that would be a binary classification kind of problem using CNN. But instead of building your CNN architecture from scratch, you can say that I will first try AlexNet. Let's see if that works for me or not. If you see that no, AlexNet has too many parameters and it is overfitting in case of in my problem, then you can easily drop some layers from AlexNet. That is very easy to do. But at least you have a starting point and you don't have to write everything from scratch. So that is the idea. That is why we are interested to know what are the recent advancements that are happening in the domain of computer science, so that we can check if their advancement can be directly applicable to physics or not. It is always a good idea to stay updated about the new papers that are coming in the machine learning domain. Okay, so this is something I believe will be discussed more in the tutorials, but I still wanted to quickly mention here that in TensorFlow Keras, you have a lot of documentation and many things that was not fully covered in these lectures. So there are many nitty-gritty details, and it was not everything was covered in this talk. So you can always read about them once you know the basics of CNN. You can always read about more advanced topics from this Keras documentation page. And this particular URL that is written here, that is the Keras applications. So these are the deep learning models that are already available in Keras, and they are available alongside the pre-trained weights. So you see the VGG model is available. VGG had two versions, 16 and 19. Linnet, I don't think is there. It's probably because it's very old. AlexNet, you can build AlexNet using Keras. I actually did not find it in this list, but there are other examples available in internet which shows how to build AlexNet very easily using Keras. There are many more, and this list actually doesn't end here. I had to crop this image to fit it in one slide. There are many more. So very clearly, the community has grown very rapidly, and people have come up with many different kinds of very deep networks, and which one you would like to try out first is up to you. But it is also a good idea to look at the HEP literature and see which of these are being used by high energy physics community. For example, I will discuss a little bit about ResNet, because ResNet is being directly used in its available form in machine learning problems in high energy, experimental high energy physics. So this can be a good starting point. There is one last thing that I want to just mention without going into a lot of details, which is 1x1 convolution. This is in its original paper, which I forgot to link here. In the original paper, they also call it network in network. I'm not entirely sure about the meaning of this name, but 1x1 convolution is something that you can use if you want to shrink the number of channels when necessary. So we already discussed that as we go deeper, as we try to build a deeper and deeper CNN, your number of channels are increasing. At every step, your number of channels are increasing, because in the convolution layer, you are using many filters, and that is why the channels are increasing. There, you will reach a point, if your CNN is too deep, you will reach a point when you have a very big number of channels. And if you want to shrink the number of channels, if you feel that this is too big to handle by the computing power that is available to you, then sometimes people use this 1x1 convolution. So 1x1 convolution is just that you have only one unit here, but it is it has the same number of depth or channels, just like what you have here. This is your input and this is your filter. So 1x1 but with the full depth of this. And clearly, if you just put it here and sum up all the numbers depth-wise and put it here, then your whole this depth is shrinked to just one cell, but you retain the width and height. So this is a completely different kind of shrinkage. All the shrinkage of images that I was speaking before, they were shrinking the height and width, and they were increasing the number of channels. Here is the opposite. You preserve the height and width and you shrink it along the depth. So this is also one concept. And the network where it was used, it was a very deep network where this was used. But because of this particular concept, the deep network did not have too many parameters to deal with. So you see in this slide that VGG has 138 million parameters, but where it was first used, GoogleNet actually did not have that many parameters, although it was deeper than VGG as far as I can remember. This type of network, so networks where we use this 1+1 convolution are also called inception network. Another thing that I would like to mention is that GoogleNet, in their original paper, it was spelled like this. The L of Google was in capital letter, so that the last part of GoogleNet becomes LeNet, and LeNet is this very first deep CNN, LeNet 5. And just to give credit to their work, because GoogleNet uses a lot of concept that was first introduced in LeNet, so that is why GoogleNet is spelled like this. Okay. Now, another fun fact is that you might wonder, where does this name inception come from? This is a convolutional neural network. Yeah, this is a convolutional neural network, and it is a very deep convolutional neural network. So what is the connection with inception? Now, those of you who have watched this movie named Inception, you might remember this scene. And this is actually a meme. They said, we need to go deeper. And this paper, Inception Network paper, or the paper that was written by the Google colleagues who came up with the GoogleNet architecture, this paper, which again I forgot to cite it, the paper actually cites this meme, this URL that is shown here. If you click in this URL, it takes you to this meme. So they didn't cite the movie itself, they cite the meme that says we need to go deeper. It's just a fun fact. Okay, so now, as I promised, I will say a few words about ResNet. This is a very cool concept, and when you are trying to build a very deep network, this comes very handy. So let's say what you see here is a general neural network with 2 layers. This has nothing to do with ResNet. This is a simple 2-layer neural network, or a big neural network, but I'm showing here only 2 layers of it. So AL is coming, activation from layer L is coming, and this is computing L plus 1, and this going to the next layer, which is computing AL plus 2. So this is generally the way to do it. We take AL, we compute the linear part of it, which is W parameter times AL plus B, which is also called Z. So the linear part is basically computation of Z. Then we apply ReLU or whatever activation function you like. Then this AL plus 1 goes to the next layer, and again we have to compute the linear part of it, which is again Z, but for L plus 2 now. So W parameters of that layer times activation coming from the previous layer plus B, and then again ready. So you see that for information to flow from AL to AL plus 2, it needs to go through all these steps in case of a usual neural network. And what ResNet does, it's called residual net, or this is a residual block. So res in ResNet is residual. What it does is that it builds a skip connection. This is called a skip connection. So you take AL and feed it directly to the L plus 2th layer. So what we have here then is that for ResNet, we will have the normal main path. Additionally, we will have this skip connection where AL plus 2 is not only ReLU operated on ZL plus 2, but we have to also add AL to it. So this is the idea of ResNet. You have the main path as well as the skip connection. So just to draw the whole network here, how a ResNet might look like. So you have the input X. This is for a plane network. You have the input X, and then you have many layers, and then you output AL at some point. But for ResNet, you have that thing. Additionally, you have this skip connection. You have repeated residual blocks that makes a ResNet. Now, the authors of ResNet, and in this case, I have put here the URL where you can find the paper where ResNet was first proposed, and they argued that so they were working with normal CNN first, and they were plotting the performance of their normal CNN with increasing number of layers. And their expectation was that with more layers, their network will perform better, the training error will go down. But in reality, they noticed that after some point, after a certain amount of layer, they found that the training error is not going down anymore. So this is what they found, and then they started to research about this and how to solve this problem, because they were dealing with a very complex data. So the data was in the form of image, but the images that they were dealing with were very complex. So complex and diverse. So that is why they could not afford to stop here. They could not afford to use a small number of layers, because the network was not, the network did not learn enough features within these layers. So they had to go deeper, and they had to find a way to go deep. And this is what then they came up with, which is called ResNet. When they make this skip connection, if you increase the number of layers, at least the training error does not increase. Depending on your problem, it might happen that this saturates here, that is, you are increasing the number of layers, and that has no good effect on your training error. So training error has saturated. It is not going down anymore. That can happen, but at least this doesn't happen in ResNet, that your training error is going up after some layers. So this is the good thing about ResNet. Okay. Now, moving on. Now I spoke a little bit about different building blocks of CNN and simple CNN. Yes.
So how can we create one data set from of this image for this CNN training?
Sorry, repeat it again. How can we create what?
How can we create kind of data set from this image for this CNN training?
Okay, so I can answer your question by describing this slide. This is, I think, one of the slides which is perfect to answer this question. Okay.
Okay.
So let's say that you have a problem in hand, which is the high energy physics problem that we are most interested in. And let's say the problem is that you want to differentiate between quark jet and gluon jet. So in detectors, once a quark or gluon enters, it essentially hadronizes and creates a spray of particles, which we call jet. And whether the jet was initiated by quark or whether it was initiated by gluon, it is sometimes important to know. So we want to differentiate between quark, gluon, jet. And how can we make the images? Is that you can it will depend on your problem. For high energy physics problem, the kind of problem that I'm discussing in this slide, you can just decide to come up with a eta phi image. So x-axis, let's say, is the eta of your subdetector. So for jets, the most important subdetector will be the hadron calorimeter, and each cell of the hadron calorimeter has some specific eta coverage, and it also has a eta number, which is generally called I eta. So let's say the x-axis is eta. If any of you is not familiar with the variable eta, then you can also think of it as the as theta. Just 1 second, I'm getting a call which I have to take. I'll be back in a minute. आज ना मेरा ऑनलाइन लेक्चर देना पड़ रहा है, तो आई विल 12:30, तो उसके बाद जा सकते हैं? ठीक 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 है, 1 बजे से Okay, sorry about that. So you can think of these jets. You can think that you have these jets and you can transform those jets into this kind of images. So where in the x-axis you have the eta variable. So the eta variable basically will tell you about the position of the jet in detector in the eta coordinate, and y-axis is phi. So basically this is the location of your jet, and the color here means what is the energy deposit. The darker color means higher energy deposit. So you can see, let's say this bottom plot that my cursor is here in this plot now, called gluon jet. So in the middle there is a lot of dark pixels, so a lot of energy is deposited here, and then as we go towards the outer region, the energy is less and less. So this is the image that you have made from your available data. So this is one way. This particular picture, this is actually averaged over many gluon jet. This is averaged over many quark jet. That is why they look so, so symmetric. Actually, if you don't average it over many jets, it will not look so symmetric. It will be sparse, and it will be more scattered and less symmetric. But in high energy physics problem, this is how you can make images for your problem. So of course, it will also depend on which area you work on. If you, I mean, for the experimentalist students, I can tell that this works very well. However, those of you who work in more theoretical subjects, I will give you at the end one link to a HEP ML review. It's kind of a repository which has all the or most of the ML papers written in HEP, both theory and experiment. There are more experiment papers than theory papers that has used ML. However, I have seen quite a few of theory papers as well. So there you can, if you are a theorist, you can look at that review repository, and then you can get some idea of how you can use ML in your particular problem. Okay. So right. So here, this particular paper, this is not any special paper or anything. This is just one paper that I had randomly chosen. There are many such papers that has
Here
been.
in case of, I have a question.
Yes.
So here in case of muons, why we are so scattered?
So we are seeing inside a jet, and generally what you will see most inside a jet is neutral hadron and charged hadron, and maybe next it is the photons. So the other particles tend to be scattered. So the leptons, so the electrons are muons. Muons are a little bit more scattered because muons are detected at the very outside part of the detector. It can be more scattered. But muons are generally less in number inside a jet than the charged hadron. If you want a similar kind of smooth looking picture for muons, you might have to average it over more number of jets to make it more smooth. Just because muons are less in number inside a jet than a charged hadron.
Oh.
Okay, so yeah, so this is not any special use case or something. There are many such use cases of CNN, and at the end of this lecture, I will actually give you all the links and everything where you can get a lot more information than this. Okay, now I think I have a few more slides, which I should be able to finish by 12:30. So this is a simple example of CNN. If you want to just try it out quickly in a problem that is, let's say, not a high energy physics problem, but you just want to try CNN out quickly using some data set that is available, then the CIFAR10 dataset is a good one. It is a widely known dataset in the world of CNN, which is also known as computer vision. It's a really cool name, computer vision. And this has many colored images and 10 classes. So this is something you can use to quickly try out what we just discussed today. And let's say you have decided to build this kind of network. And I will go very fast here because this is exactly what you will do in the tutorial. So in the next slides, I have given basically the code that you might want to write. But instead of discussing it here, it is probably better to discuss in the tutorial, which somebody else will discuss. So I will go quickly. So you have input images 32 by 32 by 3 taken from CIFAR10 dataset. Then you have one convolution layer, 3x3 filter with ReLU activation. Then you have a max pooling. Then you have your second convolution with ReLU activation. Then a second max pooling. Then you decide to flatten it out. And then you decide that you will have a dense layer. So it's a hidden layer with 128 hidden units. And that's all. Then you have 10 units in the output layer because your dataset has 10 different classes. So how can you code it up? So you can get the CIFAR10 datasets very easily. There are a few other ways to grab it. I believe this will work. And then the class names. So what is there in the CIFAR10 dataset? They have basically pictures of these things. They are plain automobile, bird, cat, deer, etc. So the first thing to do is you have to so specify what are your variables. for example, the input shape is already given, the filter size that you have decided, so you have to write that here. Filter 2 size, that is also something that you have decided, so just write that here. So like this. So these are just some variables that you are writing out at the beginning so that you don't have to input these numbers by hand later on, and you can just use this name. Then you would first load the data set, and maybe you would like to view a few images as a sanity check that the data set is actually loaded. Then you can decide to do a very quick data pre-processing. We discussed about normalizing the input features. So here you can normalize the pixel values. So a maximum possible pixel value is this. And then you can divide your training and testing images with this maximum possible value. Then, so if you're using TensorFlow Keras, then you can import the sequential model and some of the important classes that you know that you have to use in this case, like conf2d, max pooling 2d, flatten, dense. These are the basic building blocks. So you will anyway need this. So you already import these things. Then you just initialize this as, so you call this sequential class for your model. And then you look at this graph or this cartoon here, what you already decided that your CNN will look like this, and just keep adding it accordingly. So the first layer is conf2d with filter 1 size, filter shape, activation relu, input shape this. Then you add max pooling with the pool shape and so on. Then at some point when you have already done your conf and max pooling steps, then you add the, so you first you flatten, then you add the dense layer, fully connect, and this is the variable here, fully connect number 128, which was a decision that we made here. So, and then the last layer is the softmax layer with number of classes. This is 10. So I will go quickly here because this is what you actually need to implement in the code, and probably it's not very useful to see this in a slide. But conf2d class, if you need any help about what exactly is written, so you might want to know what you are using. So conf2d, you can get a lot of help and documentation. If you click on this URL, this is the Keras documentation about convolution 2D. And you can see here that the stride is already mentioned. That is why you didn't have to mention any stride related information here, because it is already mentioned, and unless you want to change it, there is no need to mention. Also, same for padding. Valid padding, which means no padding, is the default choice, and you did not change that here, so it will use valid padding. And then after that, you generally people do call the summary method to as a sanity check, just to check that everything is properly called and properly implemented. And then basically you can compile using Adam optimizer, the loss that we discussed before, which has this name of categorical cross entropy. And you can decide on some metrics, and we also discussed this decision we call accuracy, this metrics. And then you basically train the model like this. So after that, once you are done with the training, you might want to know how your model is actually performing on the test set. For that, we generally try to plot a confusion matrix. Of course, we will plot also the metrics that you have mentioned here. So you will actually plot precision, we call accuracy, of course. But in addition to that, this is the way to plot something called confusion matrix, which is a matrix like this, which plots the predicted level predicted by your network in the x-axis and the true level in the y-axis, which means that any the off-diagonal entry here means that your network has made this mistake. So ideally, we would like this matrix to be diagonal. So predicted level 5 and true level 5, so 613. But it has true level 5, but predicted level something else, that also happens. So true level 5, predicted level 0, this has happened 17 times. This is not very good. So this thing 212, so true level 3 and predicted level 5. So the network had a hard time understanding this. It thinks whatever there is in 3, it thinks as 5. So you can actually go back and see what are your 3 and 5 that your network has so difficulty to learn. So 3 would be 0, 1, 0, 1, 2, 3, a cat, and 0, 1, 2, 3, 4, 5. Cat and dog. Okay, confuses between cat and dog, makes sense. So this is the way to check the performance. And actually, that is the end of my talk. I just want to mention about the books that you can follow. So there are these 3 books that you can follow. I don't think any of them is available.
Hello,
Yes.
can you explain again the confusion matrix? I couldn't follow.
Yes. So confusion matrix is a matrix that you can plot at the testing level when the training is done and you have tested it. So you can use this model.predict this thing to your test images. So remember that when we have a big data set, we use 80% for training and then we keep 20% for testing. So you are now testing your model on these test images. And let's say you have given it a picture of a cat and it predicts it as a dog. So then that is a mistake. So this is what you see here. So x-axis is the predicted level. It goes from 0 to 9. And if you want to know what is 0 and what is 1, so 0 is airplane, 1 is automobile, and so on, bird, cat, deer. So these are the classes for which you are doing the multi-class classification. So given a picture, your network says which class it belongs to. 0 means airplane, 1 means automobile, and so on. So you want this confusion matrix to be exactly diagonal, which means if the true level, if the picture's true level is 0 or airplane, the predicted level should also be always 0. This is what we ideally want. But you can see that if the true level is 0, you have entries in every box here in the predicted level. So it does make some mistake, which means that there is some room for improvement here. But this is the main idea of the confusion matrix. It should be as diagonal as possible. Okay.
Okay. Thank you.
So about the books, these are the 3 books that I am reading lately. There are many books of machine learning, and you can choose any other book also, but it's just these 3 books it's just so happened that I bought them recently and I'm reading them right now. So I consulted them while making this set of slides. The living review of machine learning for particle physics. This is what I was discussing. Here you will get a very big list of machine learning related papers written by high energy physicists, both experimentalists and theorists. So there are even formal theorists who have used machine learning successfully in their work. And for example, there are string theory papers also that have used ML techniques, gradient descent, and so on. So it's a good thing to have a look at this. And lastly, I would like to end my talk by thanking Professor Andrew Nag So majority of the materials that I discussed in my talks are taken from Andrew's lectures, which are publicly available in YouTube. Some are available as Coursera lectures. And if you don't know Andrew, he is one of the pioneers in the field of artificial intelligence. So, and he's also a very, very good teacher, which if you listen to his lectures, you will see that he has this ability to explain very complex things in a very simple way. So that's all. Do you have any other questions?
Hello.
Ma'am, we don't have your slides actually.
Yes, I actually don't have, I cannot upload myself. I don't have the rights. I will send to Arun and then I will request him to upload it.
Okay.
Hello.
Yes.
Okay, so I think I still didn't get the answer. Like I have few images with me, and I want to create one data set out of it with some levels given to it. So how I can do that? Like
You already have a data set with some images, right?
yeah, I have let's say I have 100 images, and each image has some level with it. Let's say it's a binary kind of classification. Our example like cat versus non-cat. So how I can create the image data set with the proper labeling?
Okay, this is something that will be discussed in the CNN tutorial. So I would request you to stay tuned for today's tutorial and tomorrow's tutorial. I did explain a little bit about the code, the way you can write the code, but I did not focus too much on the first part. I think your question is related to this part, load the data set, and this part actually, which I did not discuss in detail. And this can be best done in the form of a tutorial. So there are two of them, so I think you will get your answer there.
Okay, and can you go to the slide 94?
Yes.
No, I guess 93. One slide back.
93.
No, the one where you explained the one CNN model with all these parameters and all, I guess at the 92, yes.
Yeah.
This one. Here, can you please explain again the parameters?
Yes. So the parameters is basically the learnable parameters and not the hyperparameters. So the first row is simple. Just the input, so no parameters. The second one is the convolution layer. So in a convolution layer, you have a filter, and in this case, they have a 5x5 filter. So let me pull out also our calculators so that I don't make mistake while computing this thing. Yeah. Okay, so you have a 5x5 filter. So one filter will have 25 W parameters, and then they have used 8 filters. How do I know they have used 8 filters? Because the activation shape, so after this convolution layer, they have got 28 cross 28 cross 8 matrix. So 8 means they have used 8 filters. Otherwise, this would not be 8. So 25 into 8, 200. And these are only W parameters for every
There is a bias here.
yeah, there is a bias. So there will be 8 bias. So 200 plus 8. So 208. So this is how you compute it. So exactly same computation you have to do. 25 and then they have used 16 of them plus 16 bias terms.
So okay. And why it's getting increased when we go to the deep layer?
It depends on the number of filters. You might choose to use lesser number of filters. In that case, it will not increase. But generally, what people do is that as we go deeper in the network, it is understood that now the network will be capable of learning more complex things. So it will make sense to increase the number of filters.
Yeah, that's right. But when we enter this flattened stage, So why the parameters like around 50,000?
Oh, this is like this is a deep neural network kind of layer, and here this the way I computed the number of parameters for a conv layer, that does not apply here anymore. Here it will be this NL times NL minus 1, that dimensional matrix. This is a completely different kind of computation, which was discussed in the DNN lecture on the first day. So if you have this has to be 400 size. So this is the first layer is 400 and the second layer is 120. So it's a 120 times 400. This should roughly be it for W. So let's see what is that. 120. 120 times 400. So this is 48,000, and the one is coming from the bias term. There is one bias term, and Python broadcasting will make that one B to multiple Bs, but the value remains same. So it's just one value. So
right. This activation size is the features, right? Features.
yes. So activation size is obtained by multiplying these three numbers. So these are like
Yeah.
yeah.
Right.
So 400. So when you flatten this 400, which is now hidden in the form of matrices, will be flattened out and rolled out,
Right,
and
right.
it will be like 400 blobs. So what I'm doing is that since your W matrix is NL times NL minus 1, so
Right, right,
400
right.
times 120.
Understood, right, right. Thanks. Okay.
Okay, is there any other question? Let me check in Zoom. Okay, I don't see anyone else.
Hello.
Yes.
As I told that CNN should be useful only for image data,
Yes.
but if I have some data frame with let's say 10 features and let's say 1 lakh events, then can each row be convoluted with a 1D convolutional layer or something like that?
You have your input in the form of numbers only.
Yes, data frame kind of.
Okay. Oh, I mean, mathematically speaking, since image is essentially a metric, and you also have something like a matrix, then I mean, mathematically it will work. I don't see, but it's just that people generally don't do that. People generally use CNN for images, and I also never tried to use CNN on a matrix which I know is not a image. So I actually am not sure about the performance, but technically I think it will work. Okay, anyone else? Okay, then we can stop here, and I wish you all the best with the rest of the preschool, and I hope to see some of you in the main school. I'll be there in the main school. Okay, bye bye.